Okay, guys, so in this video now, we're going to finish up chapter 10. I'm going to go through 10.7. I'm going to cover 10.8. Actually, I think 10.8, balanced chemical equations and the law of conservation of mass, already covered, guys, in the beginning of this video with formation of the water molecule. So this one you can guys now go through it yourself, yourselves. And if you have any questions, you can always ask me. But this we already guys are covered at the beginning of the chapter, guys. So now also I'm going to cover 10.9, and we'll be also covered, guys. Let me check 10.10. Yes, very important one, especially for your lab. 10.10 and 10.11. So the way I'm going to cover it, guys, I'm going to cover it all holistically. I'm going to connect all of these topics in chapter, guys, 10, just using just one example. And then once I'm finished with this example, guys, you should be able to solve each and every problem, guys, in this chapter. And again, during our online lectures, you can always ask me a question in regards to any problems. Either it's in chapter problem, or it's in the the one that is in the back of the chapter. So guys, just again, try to understand the concept first, and then apply the concept to any other problems that facing you guys. So you should be able to do them. Now, so 10.7 is the chemical equations in the mole concept. So this is what's called stoichiometry, and stoichiometry is nothing else as the mole to mole ratio. Okay, remember, guys, when I told you that this entire course here, if you know how to convert, you'll be in a really great shape. And that's why I spend so much time, guys, teaching you how to convert. Now, mole to mole ratio. Let's say we have the following equation. We have synthesis of ammonia. We got N2 gas, this is gas, reacting with the H2 gas, and it will produce now the NH3 gas, which is a very important substance because of its what it's used, guys, pervasively in as a fertilizer, and also when you can use it creating explosives. But again, I'm not gonna go into the building explosive, of course, with this molecule. But when you try to purchase a large amount of fertilizer, the FBI always want to know what the purpose of this purchase is, because you can always create some explosive from it. Now, so the synthesis of ammonia, guys, is again very important process, because this is what we use, guys, the ammonia as a fertilizer. Okay, just be aware of that. Now, so let's now start this problem, solving this problem. So let's say I have 12.4 grams of this substance here, and then I react with about, let's say, 15.2 grams of this substance here. Okay, so let's do that. And what I want to figure it out, how many grams of ammonia I can produce. But before you can proceed, guys, you always have to make sure that the chemical equation is balanced. Very important, guys. Always check. Now, I can see right now, just by examining this equation, it's not really balanced. You got two nitrogens in here, two atoms of nitrogen, or 2 moles of nitrogen atoms. And then, so what you have to do, you have to balance nitrogen. 2 times 1 will be 2 now. But since I put the 2 in here, I have to now do the distributive property for hydrogen. 2 times 3, 6. And then this becomes 3 in here to make it 6. So now this is a balanced equation, guys. Now I can find out everything that I need to find out. Okay. Now, so how do you solve this problem? So let me just move these numbers a little up here, because I will need some space, guys, to solve the concepts in here. And let me just erase this here in the bottom. And let's start solving this problem. So again, my goal here is to find out if I have so many grams of nitrogen. Oh, let's do this first. Let me just tell you this. Let me just do one thing at a time. Let me just say this will be excess here. Excess. In other words, will be unlimited supply. And then I'll get to the other type of problem, which is called limiting reactor problem. This is unlimited supply, let's say you have, of hydrogen. Okay, so how would you solve this problem? Because this one has an unlimited supply, that's why I don't, I don't pay attention now how many grams I got here, just unlimited. Now, what's important here to realize that these coefficients here, what's called mole-to-mole ratio or stoichiometry concept. So what I'm trying now, to explain you guys is this coefficient has very, very significant importance here. Now, look, what I can say now is that if you react 1 mole of N2, right? You always have to react it with 3 moles of H2 to produce now the 2 moles of this ammonia here. Now, how can we relate it now to something like from the micro world to the macro world, like to something we can see? Is if you're building a table, and when you build a table, you always want to use 4 legs plus 1 top to produce a table here, right? So you got a table. So in other words, you got 4 legs, and this is the 4. It's like a coefficient here in the chemical reaction here. This is 4 legs reacting now with 1 top. And this is, let's say, similar now to this coefficient, let's say. And now you produce 1 yields 1 table. So in other words, if I have, for example, 20 legs and I have excess amount of top, I have a bunch of these tops in here. Now what's gonna happen here is that I can only produce, let me see how many tables. 4 legs, 4-to-1 ratio, 4 legs, right? I got this 4 from here. 4 legs will be always, ratio will be to 1 table. And that's what's called mole-to-mole ratio in chemical reaction, this ratio, 4-to-1 in this case. In our case, it will be 1-to-3, 1-to-2, 3-to-1, 3-to-2, etc. So I'm gonna write all of these mole-to-mole ratios in a moment, but let me finish this one now. So we have 20 legs and excess number of tops, right? So all I can get now, I can only build now 5 tables. Only 5 tables, guys, can be built. Now, what happens if now I have, let's say, 20 tops and I have excess amount of legs? Of course, if I have 20 tops, let's say, and I have excess amount now of legs, I know my mole-to-mole ratio here is 1-to-1 here. Again, I'm kind of trying to, guys, show you how the macro world is very related to the micro world, to the molecules, because when you build the molecules, they all have fixed composition. For example, this nitrogen triple bonds, 1 molecule, when it reacts with 3 hydrogens, of course, guys, remember you have to break the bonds of the reactants. And so what you're forming here now, look, I got 1 of the nitrogens will be used now to form 1 of the ammonia molecules, and there is another one right here will be used now. So in other words, look, guys, look, this is 1 of my nitrogens right here, 1 of my nitrogens now right in here, and then the 3 of my hydrogens we use now to build 1, 2, 3, and now the other 3 hydrogens, 1, 2, 3. See? These numbers are very important because they give you these fixed ratios, or they called, of course, ratios or conversion factors. So all I'm doing right now, using again similar to now to my table, these numbers here, there are conversion factors here. So I got, of course, 1 table is related always to 1 top when you build a table. And so this and this cancels out, and you'll be able to build now 20 tables. Okay, so this concept with the tables, very similar, guys, to the concept here I'm trying to explain what stoichiometry is all about, or mole-to-mole ratio. It's another term to use. All right, so let me erase now all of this. Again, guys, you got a video. You can always go back and check, my explanation here. So I don't have to keep it here. I just need some spot, guys, in here. In other words. All right, let me just erase everything here. That doesn't want to get erased. Okay, there you go. Finally, we got to erase it. All right, so Let me erase also this, because now I have to do the calculations, guys. I have to produce now my multiple ratios here. I'm going to put them here in the corner so that I can always use them here. All right, so here are my multiple ratios. I got every time I need to build 2 molecules of ammonia, I always need to say 1 mole now here, because this 1 stands for 1 mole, right? Or 1 molecule you can use also. But because we're given grams, so we're dealing with the moles here. So 1 mole now of N2 always needed, guys, to make 2 moles of NH3. Now, 3 moles now, let's say, of H2 always needed to make 2 moles of the product, right? And so another one, 1 mole now of N2 always, guys, going to be consumed with 3 moles of H2 to make the 2 moles of NH3, okay? So these are very important conversion factors. And of course, you can, guys, represent them as ratios as 1 mole of N2 divided by 2 moles of NH3. And you can also flip it. You can say 2 moles of NH3 divided by 1 mole of N2, depending on what you need to convert it to. Okay, so let's do the conversions now. So I'm going to convert now the grams of this, eventually into the grams of this. And watch me how I'm going to do it. Remember, guys, chapter 9, when we do the moles conversions and everything, this is where it comes now to play, all of this knowledge. All right, let's do it. So I need at the end the mass of my product of NH3. Okay, so how do I get it? I always, guys, state what's given. I'm given 12.4 grams. When I do conversions, I always, guys, want to now state what's given first. And then the next thing I want to do, guys, I want to find out what's the question is all about, right? In this case, the question is how many grams of the product I'm going to form. And that's what I just written here so that I know, guys, when I convert, I know the units that I'm going from to going to, guys. I know now, you know, what the question is, and I know what's given. All right. So the first step to get from here to here, of course, guys, I will have to use multiple ratios. So you have to get the moles, guys, first in the first step. I'm going to say that 1 mole of N2, you see the substance must match the identity of it. So 1 mole of N2, so you're going to go to the periodic table, and you're going to find out, 1 mole of N is 14.01. But I got two moles of this atom, right? So I'm going to say now 28.02 grams of N2, canceled. Okay, so now I got the moles unit here of N2. Is that what I want? No, I have to keep on going. So now, guys, I can choose one of these conversion factors to get to the moles of this substance here. Once I get there, I'm almost, guys, solve the problem. Okay, let's do it. So looks like this will be my conversion factor here because it contains the 2 substances that I'm interested converting from one to the other. All right, so let me go now to my balanced chemical equation and see where did I get 1. Oh, there it is, the coefficient, guys. That's where the coefficient now is in play. I'm going to say 1 mole. Remember how there was 4 legs of the table producing 1 table. So 1 mole of N2, always producing. Now you got this 2 here. 2 moles of NH3 here. Okay, canceled. Now look, I'm almost there. I already got the substance I really want. So now I need the grams. How do I do this? Well, to do this, I just have to convert. I know that now 1 mole of NH3, oops, let me just erase this. So now 1 mole of NH3, and I need to figure it out now how much it is equal to. So I go to periodic table, and I know that 1 mole of NH3, you just have to know I have the 3 times 1.008 plus 14.01. Looks like it's going to be 17.03 grams of NH3. Okay, so I'm going to cancel this. I'm going to cancel. Let me just real quick, guys, check that 17.03 because, again, I'm doing it on the fly. So 3 times 1.008 plus 14.01. Okay, yes, 17.03. That's correct. And look what happened here, guys. Now, very important here. I got grams of NH3 matching with the grams of NH3. Guess what? I'm finished with this problem. So the only thing I have to do now is to do the proper calculations, guys. I have to carry the proper calculation here. I have to say 12.4 grams. I can multiply now by 2, then multiply by 17.03, and then divide, guys, by this number because it's in denominator. All right, let me do it. So I'm going to do 12.4. Now multiply by 2. Then multiplied by 17.03. And then divided by 28.02. All right, so I got my answer. Now, guys, remember here I'm going to do now significant figures because now the calculations here are important. In the previous example in the beginning, guys, of teaching you guys 10.1, 10.2, I kind of neglected significant figures because I just wanted to show you guys the concept of conservation of mass. All right, so here you got 3 significant figures. And this is exact number, infinite number of significant figures. This is exact number, exact number, exact number. And this one has 4 and this one. So now we're going to express final answer with the 3 significant figures. So that looks like it's going to be 15.1 grams. Okay, so what did I just do, guys? Well, what I just did is, if I'm given, guys, 12.4 grams of ammonia, my apology, of nitrogen gas, and I'm reacting it with excess amount of hydrogen gas, I should get 15.1 grams of the product. So without doing any experiments, what I just did, I just found the theoretical yield, what's called theoretical yield. So this is, guys, in the perfect world, theoretical yield. If your reaction convert, guys, into 100% from these elements into this compound, you must get no more, guys. This is the maximum you can get. This is 100% you can get. 100% will be 15.1 grams. But in reality, this reaction really does not go that easily to completion. And usually you get about 50% of the product here. And so what this reaction, guys, what they do for this reaction is they use a catalyst in this reaction to make more product. But also one of the ways you can make more products here, you can use Le Chatelier concept, which we're not going to cover in this, I guess, in this course. But as this gas is being formed, you can actually remove it so that you can shift the equilibrium to the right, making more and more product as these reactants, guys, are colliding and forming the product. Now, you can now do the same thing now for hydrogen. If you're giving, guys, a certain amount of grams of hydrogen, and then you give an excess amount of nitrogen. And so all you have to do now is to convert now the grams of hydrogen into the moles. And instead of using 1 to 2 mole to mole ratio, you're going to use now the 3 to 2 mole to mole ratio. So that now this will give you, guys, the number of grams of ammonia gas produced based on that certain amount of hydrogen gas, assuming that the nitrogen, guys, you have excess amount of nitrogen. So all of these problems are very typical. Usually you're given a certain amount of either one of the gases here, and the other one will be either explicitly stated its excess, or they will not mention it. And so you will have to assume, guys, as long as you have just one amount for one of the gases, then you have to assume that the other one is just excess amount. Okay, so I just, guys, explained you how to find out, guys, how much mass of the product you'll get at the end of the reaction, given the amount of one of the reactants, using what's called stoichiometry or mole-to-mole ratio concept. Now, in the next video, what I'll do, guys, is that also this is what's called theoretical yields. This is the maximum amount of the product, guys, you can get by reacting 12.4 grams of nitrogen. So in the next video, what I'll do is I will cover, guys, now what's called the limiting reactants. And I will wrap up this with the next video, guys. We'll actually cover now what's called theoretical practical yields. And that will be the end of chapter 10. All right, so guys, I'll see you in the next video.